Hello. In this video, we discuss how to write formally a logical argument, as well as analyze it using truth tables and standard forms. Let's get started. So to begin, we describe an argument as something containing statements that are assumed to be true. We're going to call those statements premises or premises, and a conclusion. So you have a premise followed by another premise, and in fact you can have more than two premises, followed by a conclusion. Now we consider this to be a valid argument if the conclusion flows logically from its premises. Okay, so sometimes you'll hear an argument made where there are some premises, but they don't actually logically force the conclusion to happen, in which case that's not a valid argument. But let's talk formally how we set these up and analyze them with truth tables. The first step you want to do in your little three-step process here is represent each of your premises symbolically. So using your P's and your Q's and your symbols that we've studied in former videos. The second thing we want to talk about is how do I actually set up a truth table that would help me to verify the validity of an argument. And the way we're going to do that is to work toward a conditional statement. Remember, that's an if-then statement. By joining all of your premises, so for example, I'll use P for premise. So premise 1 with the word and. So that's our conjunction, like our upward arrow, and premise 2, P2 for premise 2. And again, you can have more than two premises, but you need to connect all of your premises together as a conjunction. So premise 1 and premise 2, and if there was a premise 3 and premise 4, et cetera, et cetera. But assuming that you just have the two of them, you want to group them up using your parentheses. So we're saying that is our antecedent of our conditional statement. So if this condition happens, then something should follow. So we write our arrow next, if then. What should follow? The conclusion. And I'm going to use C for conclusion. So this is the basic setup that we're looking for in our truth table. We want to have an if-then statement. If my premises all happen, so if premise 1 and premise 2 and premise 3, however many premises we have, if they all happen at the same time, then the conclusion should follow logically. Okay, so that's our second step. We want to build a truth table for that column. Our third step then in the truth table is to verify whether or not we have a tautology. That's really the question here. Using a lot more words than that, right? Is it a tautology? If it is a tautology, that means that the final column is always true. In other words, these premises always force this conclusion to follow. When the premises happen together, the conclusion logically follows. If they're always true, then the argument is said to be valid. Now, we'll talk more in later videos and toward the end of this video about what happens if your premises weren't true to begin with. But right now, we are assuming your premises to be true. Okay? So let's take a look at the example that's on this same slide. It says premise, we could call it premise 1. Premise 1 says, if I go to the mall, then I'll buy new jeans. Okay? So what we notice here is that we've rewritten I go to the mall as our first logical statement. Usually we use P's and Q's. Here they've chosen to use M for mall, right? So if I go to the mall, then I'll buy a new pair of jeans, or I'll buy jeans. We've let that be statement J. So our first premise, P1 if you will, could be rewritten symbolically, and that's what we're supposed to do first here, by writing M for if I go to the mall, arrow, so an if-then statement, J, I buy new jeans, okay? What about premise 2 here? Premise 2. If I buy new jeans, then I'll buy a shirt to go with it, okay? So if I buy new jeans, then I'll buy a shirt to go with it. Well, buying new jeans was already letter J, and this is an if-then statement, so you can see how they've written our premise 2 here symbolically as J, arrow, S, where S was the statement, I buy a shirt, or I buy a new shirt. So now we have premise 1 is M, then J. If M happens, J should follow. Premise 2, if J happens, S should follow. The conclusion here that we're seeing, described here, our conclusion, is that if I go to the mall, then I end up buying a t-shirt or a shirt. So our conclusion, symbolically, is we're typically going to use these three dots that look like a triangle. This is formal, in formal logic, this is the symbol, the triangle of dots there, that means therefore. So we're saying therefore, our conclusion should happen. What is our conclusion? If M happens, then S should follow. So if I go to the mall, then I should end up buying a new shirt. Okay, so this is what we call a formal argument in symbols, okay? if M then J, if J then S, therefore M then S. Okay. Now it turns out this is one of our standard forms that we'll be discussing in a future slide, so get ready for writing out some standard forms that you'll be memorizing to go faster. But when we don't recognize things as standard forms, we have to build a truth table, okay? So here is where we're at with step 2 here. Step 2 in our steps above was to create a conditional statement joining all of the premises with an and, or a conjunction, to form an antecedent, and then use the conclusion as your consequent. So in this case, notice that the statement for premise 1 was right here, if M, then J. So that's premise 1. And premise 2 was if J, then S. So that's premise 2. Putting those together, you can use parentheses or brackets, whatever you want to group them together. That should imply that the conclusion, a lot of words start with con, the conclusion should follow, okay? So this is what we are ultimately trying to work our way up to, and that's what you see here in this column right here, the last column. We have premise 1 and premise 2 together as the antecedent and the conclusion as the consequent. And the if-then part is because we're saying our premises together should force this conclusion to happen. All right, so what they did then is they made their truth table with half truth and half falses for your first column for M, and then 2 by 2 like we did in our previous videos, and then 1 by 1 for S. Next up, they wanted to find the premise 1 column, which was if M, then J. And remember, for an if-then statement, the only time that that is false is if the first is true, but the second is false. So here, the first was M, and the second was J. So whenever the first was true and the second was false, that's where we saw our falsehood. And that happened in the 3rd row and in the 4th row, didn't it? And then same thing, same idea for finding the second premise. If J, then S. The only time that will be false is if J is true and S is false. Is J ever true while S is false? Yeah, in the 2nd row we see that happening. And again, down here in the 6th row, we see that happening. Putting them together, that's going to be our antecedent of our big statement we're trying to build to see if this argument's valid or invalid. So we put them together with the and connective. And what had to be true for an and statement? You can look back in your notes if you forgot. That's right, they both had to be true. So looking at these two together, when are they both true? They're both true in the first case, and then that doesn't happen again until the 5th case, the 7th case, and the 8th case, okay? So now this would be the column that represents our antecedent of our big conditional statement right here, okay? So now we have that column ready to go, but we need our consequent statement here, which is if M, then S. So how do we do that? Well, we looked at the M column first and the S column second, and it's going to only be false when M is true while S is false. Does that ever happen? M is true while S is false? M is true while S is false. That happens in the 2nd case, doesn't it? In the 2nd row, and also in the 4th row. So we have those two falsehoods. Other than that, it's always true. So now we have our column for our consequent. To put those two together then with a conditional statement, we say when our first is true and our second is false, that's our falsehood. Let's see if that ever happens, okay? Looking carefully at our antecedent, which is first here, and our consequent, which is second. For our antecedent right here, this is our first one. That is true here in this case, but it's also true for its consequent, so that's okay. It's true again here in the 5th row, but it's also true for the consequent, so that's okay. It's true in the 7th row, but it's also true for the consequent. It's true in the 8th row, but it's also true for the consequent. So there are no falsehoods here, which means this entire column is a tautology. If it is a tautology, then we have a valid argument. So this is in fact a valid argument. And it's one of the forms that we're going to recognize as we get more comfortable with formal logical arguments. And this will actually be looked at in a future slide. So we're going to come back to this one. So make sure you make a note on this slide to come back to it with this fancy name that we're going to learn about. When you're ready, let's head to our next slide. So speaking of standard forms to recognize, here are 4 valid argument forms that you'll want to memorize, as well as 2 invalid arguments or fallacies. Let's look at the first 4 and make sure again that you make flashcards or find a way that it works for you to memorize and recognize these forms. So for our first form, we call this the Law of Detachment. So what is the law of detachment? Well, the basic idea here is for premise 1, you have an if-then statement. So here's premise 1, if P, then Q, okay? But for premise 2, you only have the antecedent. So we take this antecedent here and we see it again. So for example, this could be the statement, if I do my homework, then I pass the class. That's premise 1. Premise 2, I did my homework. Therefore, what conclusion should follow? I should pass the class, and that should make logical sense for us. So the law of detachment basically is the case where you have a conditional if-then statement where the condition is met as your second premise. Therefore, for your conclusion, you should have your expected outcome or your consequent from the original premise. So whenever you see that, you don't necessarily have to do the work of performing the entire truth table. If you were, you would have had to have premise 1, which is P, then Q, and premise 2, which is P, and then you would have to see if that always implies your conclusion. If that's a tautology, that statement's a tautology, then it's a valid argument. But rather than doing all of that, it's a lot easier just to say, oh, I recognize that. That's the law of detachment, so this is a valid argument. Another one that you'll want to notice, pay attention to, is what we call the law of contraposition, or the law of the contrapositive. That's something we've talked about in a previous video. Do you remember what the contrapositive did if you had an if-then conditional statement? That's right, we said it was equivalent. You can go back to our equivalent statements video. If you took the antecedent and the consequence, if you flipped their order, so one became the other, and then negated them individually. So if P then Q was equivalent to if not Q, then not P. So look and see, that's what's happening here. Someone makes the statement for premise 1, if P then Q. And then for premise 2, not Q has happened. Therefore, not P should follow, because we know that the contrapositive was not Q implies not P. Remember, that's what we called our contrapositive. So that one should be familiar to you. So here we're saying if you have an if-then statement and the negation of the consequent has happened as our second premise, then the negation of the antecedent can be expected as our logical conclusion. So whenever we see that one, we can just say that is valid by the law of contrapositive or law of contraposition, okay? Now notice that the order matters, right? This was not Q and then not P was the conclusion, not the other way around. The next one that we want to pay special notice to is called the Law of Syllogism, and this one might seem familiar based on our previous example. It says for our first premise, if P, then Q. For our second premise, if Q, then R. For our conclusion, therefore, if P, then R. Now this seems to flow logically, almost like you're dealing with dominoes, right? The game of dominoes where you have them all lined up, not the game where you're actually competing for a score, but where you're actually trying to knock them all down, okay? So if you have a domino followed by another domino and then another one, and they're in such a way that they're going to affect one another when one falls, if the first one falls, because it hits the second one will hit the third one. So in reality, the first one causes the third one to fall. And that's what we see here, as long as your consequent for your first premise is the same as your antecedent for your second premise. So as long as those are the same, that's like having the middle domino that will force the third one to fall. So P forces Q to fall, and then Q forces R to fall. So in reality, P has forced R to fall. So this is called the law of syllogism, and if you go back to our previous slide, you'll see that that's exactly what we were dealing with the going to the mall and buying a t-shirt example. Okay, so we didn't need necessarily to do the truth table. We could have simply recognized, hey, that's the law of syllogism. We're going to just say that that is valid. Finally, we have another one to memorize, and this one is called the disjunctive syllogism. Now, if you think back to your previous videos at the very beginning of this unit, we talked about a disjunction being an or statement, and we usually use that V, right, V shape. And so that's what we see here. For our first premise, or for at least one of the premises, you should have an or statement. So if you have an or statement, which is different than we've seen before, the first three were all conditional if-then statements. But if you have an or statement, and then for your second premise, for another premise, one of them, that's something to put in your notes here, one of those two statements that were above is now negated, okay? That must mean something to us, right? So someone has made the promise, this is happening or this is happening, right? I like Coke or I like Sprite, something like this. For the second premise, someone says, oh, she doesn't actually like Coke. What does that mean then? She must like Sprite, okay? And so that is a disjunctive syllogism. If you know one of two things must happen, this or this, and then someone tells you, oh, this one thing that we mentioned above, one of those things didn't happen, then the other thing must have happened. That's kind of logically clear, hopefully, for you. So notice here, it doesn't have to be not P. It could have been not Q. In that case, P would have had to happen, right? So if one of them is not happening, then the other one must happen. That's going to be a valid argument every single time you see it, okay? Now there are two arguments here which are always invalid, okay? And let's see why that is. These are called the fallacy of the converse and the fallacy of the inverse. Well, if you remember, when we talked about equivalent statements in a prior video, we said that if we simply flipped for an if-then statement, the P and the Q, or the antecedent and the consequent, if we simply flipped them, like Q implies P, that was called the converse. And remember we said that that was not equivalent to the original statement, right? To P, then if P, then Q. And similarly, we also said if you had simply negated the original statement, so if you had if P, then Q, and you negated each piece, not P, then not Q, that was called the inverse of the original conditional statement. And we also said that that was not logically equivalent, and we could prove that using a truth table because they're not the same. Because those two are not equivalent to the original conditional statement, it follows that the following arguments are also invalid. And let's see why. If you have an if-then statement, like if P, then Q, and then for your second premise, you have the consequent. Notice that's not the same thing we saw over here where we had for the law of detachment, we had the antecedent next. But now we have the consequent. Does that force necessarily the antecedent to happen? No, because that's basically saying, okay, you know that if P happens, Q should happen. Well, Q happened. Does that mean that P has to happen? No, because that would be the converse, which does not mean the same thing. It's not equivalent to the original if-then statement. If it was the contrapositive, however, that is equivalent to the original statement. So that's why law of detachment, valid. Fallacy of the converse, invalid. Similarly, the fallacy of the inverse works very much the same way. If you have an if-then statement that says if P, then Q, and then you just take the negation of your antecedent, like we do here, not P happens, and then say, well, does that force, therefore, not Q to follow? No, because notice that's just really the inverse of the original, not P, then not Q, which is not the same thing. It's not equivalent to the original conditional statement. So these are the two which are invalid. These are the four which are always valid. So you'll need to recognize them, and you'll need to be able to identify them as valid or invalid, and for which reason? By the law of whatever, or the fallacy of whatever. So make sure you memorize those and are ready to save time instead of doing a truth table. All right, so let's take a look now at this example on the slide below. I'll make some space for us. All right, so we see for this example in words, we are told the following. I will go to class, or I will sleep in. I did not go to class, therefore I must have slept in. All right, it's kind of simple, but let's see if we can unpack this. So first step, you can look back to your last slide. When you're analyzing a logical argument, you want to rewrite the argument symbolically. So symbolically, let's first recognize going to class, or I will go to class. That's like statement P, right? Again, you could label it C for class if you preferred, if you like that better from the last example. But most of the time we use P's, Q's, and R's, etc. So going to class, or I will go to class. And Q would be sleeping in. I will sleep in, or I slept in. The tense doesn't really matter here when you're identifying it. More of what is the basic verb happening, sleeping. I slept in. Okay. Notice we repeat the same verb here. I did not go to class. It's just negation of P. So that's already understood. And I must have slept in. That's the same as sleeping in. So that's just Q. So let's see how I could write these statements symbolically now as a premise, and a conclusion. And again, in real life, people making arguments for something will typically have many, many premises that are stacked up on top of each other to lead them to their conclusion, right? This is one reason, this is another reason, and hopefully they're all logically connected so that the conclusion follows. All right, so let's take a look here. We have premise 1, I will go to class or I will sleep in. So that would be P or Q. Notice that is a disjunction. So if it's going to be any of the standard forms above, the only option here is the disjunctive syllogism because the rest are if-then statements, right, for their premise 1. For premise 2, it says, I slept in. Is that right? No. Actually, premise 2, I looked at Q by accident. Premise 2 is right here. I did not go to class. So statement 1 was our premise 1. Statement 2 was, I did not go to class. So that would be the negation of which letter? This is really important. It's P, right? Negation of P. Okay, so typically we put a big line underneath our premises, and then we have our conclusion with our little triple triangle of dots here. Therefore, what should be the conclusion? I must have slept in. So that would be letter Q, we said. Now, if I can recognize that this is the standard form of one of the 6 above, then I already know that this argument is valid or invalid without having to do a truth table. But you're welcome to try a truth table just for practice. So in this case, premise 1 seems to match here. Premise 2 matches as well, and the conclusion matches. So I would say that this argument is valid by the disjunctive syllogism, standard form. Now notice here what they could have done instead. They could have said for premise 2, I did not sleep in, and for the conclusion, they could have said I go to class or I went to class. That would also work, right? As long as they have negated one of these two, and then the other one happens, right? That is a disjunctive syllogism. If you want to try this one as a truth table just for practice, because sometimes they don't fit nicely into one of these 6 forms, you would have had to do premise 1, which in this case is P or Q, and premise 2, which in this case is negation of P, and that whole thing, once you put it together, is your antecedent, and your conclusion is your consequent. Your consequent, in this case, would be the letter Q, right? That was our simple conclusion. If this is a tautology, when you get to this final column, it'll take some time to get there, then you can say that this is, in fact, a valid argument. Okay, but that takes some time, which is why if you can recognize a standard form, you save yourself a lot of time. All right, when you're done with this slide and you have everything in your notes really clean and you make your note cards and you're ready to go, then head to your next slide for some practice. Try this one on your own. Pause the video and see how you do. It says determine whether the argument is valid or invalid. Notice we're not saying true or false. That would be if we had a statement. A statement can be true or false. Here we're saying, does this argument flow logically from the premises to the conclusion, assuming that the premises were true. Okay, so let's take a look at premise 1. It says, if I have a shovel, I can dig a hole. So we have an if-then statement. So if I was writing this symbolically, maybe having a shovel could be letter P, digging a hole could be letter Q. So let's see if you did the same as me. So for my first premise, I have for premise 1 here, if P, then Q. Okay. For premise 2, I dug a hole. Well, that was just letter Q, wasn't it? It was. So for premise 2, we have the simple statement, lowercase q here. Okay? Then I draw my line since I only have 2 premises this time. My conclusion is, therefore, I must have had a shovel. That's the lowercase p. Okay. So let's see if we recognize any of the standard forms here. Okay? We have an if-then statement originally, so that definitely could have been one of the law of contrapositive, right? That could have been an option. It could have been a fallacy of the converse, fallacy of the inverse. So let's take a look at what we actually have here. For our second premise, we have not the antecedent, but rather the consequent. And then for our conclusion, we have the antecedent. In other words, if Q, then P. Do you remember what that one's called? That's called the converse, right? So this is actually the fallacy of the converse, which means this should be logically invalid. But since they gave us a truth table just for practice, let's go ahead and do it the long way. Otherwise, we would have normally recognized this as a fallacy of the converse and called it invalid. So let's see how our truth table would have looked. I'll use blue for my truths here. So P is true, true, false, false. And Q is true, false, true, false. You can go back to our previous videos if you still have trouble setting up your truth tables. Feel free to check those out. Okay, now I need to write a column for every simple statement until I build up to my final one. Where are we going, though? So you need to have a plan, okay? Your plan is to have premise 1 and premise 2. Again, if there are multiple premises, you'd have them all together in parentheses with a conjunction, implying your conclusion. Okay? So let's see if we can do that. What is premise 1? Well, premise 1 is P then Q. So P then Q, that would be what we call premise 1 here. Okay. Premise 2 is just the letter Q. So this is premise 2 here. And the conclusion is just the letter P. So that's our conclusion here. Okay? So typically you have to work a little harder, but in this case, a lot of them are already known. So what are we going to be doing in our column next to, or basically our fourth column? What are we going to be doing? We're going to be putting premise 1 and premise 2 together before we actually make the final column here, the if then. So for if P then Q, remember that that is only going to be false when the first is true, but the second is false. So in this case, when P is true and Q is false. And that happens only in the second row. So that's our only falsehood. Everything else has to be a truth then. True, false, true, true. Go back to a previous video if you need help with that. For the next column, when we put the two premises together, premise 1 and premise 2, let's make sure we do that correctly. Let me grab a color here. Premise 1 is this column here. Okay, premise 1. And premise 2 was right here, Q, right? So that's going to be premise 2. So putting those two together, let's see what happens. When is an and statement true? When they're both true, that's right. Which happens in the first case, right? They're both true there. And in the third case. But in the second and fourth case, that does not happen. So that's our falsehood and our falsehood. Okay? Finally, after you put your premises together, premise 1 and premise 2, you want to see if they force the conclusion to happen, right? Do these premises result in this conclusion? So if these premises happen, does this conclusion follow? So let's see if we can build our final column here. So this is our antecedent here, this column here. So this is like our first one. And our second one is our conclusion, which was just the P column, according to what we had right here, right? All right, so this is our second. So again, an if-then statement is only going to be false if the first is true and the second is false. So here the first is true and the second is true. Well, that's okay. Here, going to the third row, the first is true and the second is false. That's a problem, right? That's going to be our falsehood here. The rest of them are true by definition. So true, true, false, true is our final column. And the question you have to ask yourself when you're checking whether or not this was a valid argument when using a truth table is, does your final column, which has the premises together as conjunction, implying the conclusion, is that always true? Is that a tautology? And it is not. Since it is not a tautology, we would say that this is logically invalid. And the reason is because it's not always true, right? Your premises together do not always force this conclusion to happen. And that would be the same thing that we would have seen if we had noticed that this was the fallacy of the converse. And that would have saved you a lot of time, right? So this is another way you would have known that we had an invalid argument. Okay, when you think you're good with this one, try the next one on your own. Example 2. Determine whether the argument is valid or invalid. Premise 1. If I work hard, I'll get a raise. Premise 2. If I get a raise, I'll buy a car. Conclusion. If I don't buy a car, then I must not have worked hard. Ooh, that sounds a little harsh. And the question is this argument valid or invalid, right? Does the conclusion flow logically from the given premises, assuming that they're true? Okay, so the first thing I hope you did when you paused the video and tried it on your own was to rewrite these premises and the whole entire argument in logical symbols. So working hard could be letter P, for example. Getting a raise could be letter Q. So again, here we see getting a raise, so that's still letter Q. Buying a car, that's a new type of statement, right? We had working hard, we had getting a raise, and now we have buying a car. So I'm going to call that letter R. And then finally, in the conclusion, we're talking about not buying a car. Well, that was already discussed as R, so that's a negation, right? And not working hard, which is a negation of P. Okay, so to write this symbolically, our premise 1 would be an if-then statement. If lowercase p, then lowercase q, right? If I work hard, then I'll get a raise. Again, you might disagree that this is true or false. We're assuming it's true, and we're for the spirit of analyzing whether, if this was true, if the premises were all true, would this logically force the conclusion to happen? That's what we mean by valid or invalid here. So if I work hard, then I get a raise. Okay, premise 2, assuming it's true, what do we have in symbols? If I get a raise, so that's letter Q, then I'll buy a car. That would be letter R. Okay, there's no other premises that are given, so we'll draw our line here. And then our conclusion is, therefore, if I don't buy a car, so that's a negation of which letter? Careful. Negation of R, good job. If I don't buy a car, then I must not have worked hard. Well, that's the negation of what letter? P. Okay. So this is our symbolic argument for this problem. Okay. So if I recognize it as one of the standard forms, do I need a truth table? Nope. I would know it's valid or invalid by one of those forms. And maybe you recognize here that it appears to be one of our forms right away. If P, then Q. If Q, then R. Remember, if those two line up, if your consequent of your first premise and your antecedent of your second premise match, this is like the domino effect. This could be a law of syllogism situation. What would we expect the conclusion to be here? That's right, if P, then R. So we would expect if P, then R. If it was that, then this is a valid argument, right, as our conclusion. But what is our actual conclusion? If not R, then not P. Well, if those two are equivalent to each other, then we are done. Then this would be valid by the law of contrapositive. But are they? Well, actually, if you think about it, if I flip P and R and I negate them, what do I have? Not R, then not P. So aren't these two actually what we call equivalent because they are contrapositives? Yeah, they are. So this is a law of syllogism because the conclusion here means the same thing because of the contrapositive as what we expected it to be. So yes, we actually do know that this is a valid argument if we're a little bit careful there, but because they didn't expect us to do it that way, let's go ahead and do it the long way for practice. So the first thing I would notice is that there are 3 simple statements. Hopefully you did as well. P, Q, and R, so there are going to be 8 rows. For the P column, half true, half false. True, 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 true. Followed by 4 falsehoods. False, 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 false. For the Q column, true, true, false, false, true, true, false, false. And for the R column, true, false, true, false, true, false, true, false. I got a little lazy with my pen here. Let me catch up with you. True, true, false, false, true, true, false, false, and then R is true, false, true, false, true, false, true, false. Okay. Next up, what I would recommend is figuring out where you're going, right? Don't get stuck in the details if you don't know where you're going. Remember what we have to have if we're trying to show that an argument is valid or invalid. In a truth table, we need to have premise 1 and premise 2, right? In parentheses, right? Grouped together. Arrow, so that means if the premises happen at the same time, the conclusion should follow. Arrow, conclusion. So we want to make sure we have a column for the premise 1, for the premise 2, for the conclusion. Sometimes we have to build that ourselves, and let's see what we have to do here. For premise 1, we need if P, then Q. Okay? So for premise 1, I need if P, then Q. So that's good. For premise 2, I need if Q, then R. Okay, so this is premise 1. This is premise 2. And then I want to put them together with an and. So premise 1 and premise 2. I need to put them together. What else do I need to do? I need a conclusion column, don't I? Now, the conclusion column in this case was negation of R, then negation of P. Now, if you're clever, you could notice that's the same thing as P then R, but assuming you hadn't seen that, you would need a negation of R column. You would need a negation of P column, and maybe you'd done those at the beginning instead. That might have made more sense since the chart is a little bit bigger that way in this case, but you know, we can do it in different orders. And then finally, you would need the conclusion itself, which is negation of R, then negation of P. Okay, that would be your conclusion column. Okay, so you're working your way up to build to the last column. So let's see how that works. For our premise 1, the if P then Q, remember that's only false if the first is true and the second is false. So when P is true and Q is false. When does that happen? Looks like that happens here in the 3rd row. P is true and Q is false. So that would be a falsehood there. Let me get my red color here. So P is true and Q is false. That's going to be a falsehood. And that happens again in the 4th row. P is true, but Q is false. So that's a falsehood. Everywhere else, though, that premise should be true. So true, true, false, false, true, 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 true. For our second premise, if Q then R, again, that should only be false if our first is true and our second is false. And let's see when that happens here. Let me erase that just for now. Let's see where that happens here. So is Q ever true while R is false? Is Q ever true while R is false? Yeah, it happens in the second row. Q is true and R is false, so that's a falsehood. It happens again in the sixth row, because Q is true while while R is false. Lots of letters here. So that would be a falsehood there. So everywhere else should be true for that column. So we have true, false, true, 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 false, true, true. That's if Q, then R. That is premise 2. Now to build our conclusion, we had to get the negation of R and the negation of P column. But before we do that, you might want to find this piece of the final statement, which is premise 1 and premise 2 together. So let's do that. Premise 1 and premise 2 together with an and. When is an and statement true? When they're both true. That's right. That happens, notice, in the first case, true and true. So that is a truth. And it happens again here in the fifth case, true and true. Also in the seventh case and in the eighth case. So those should be truths. The rest would all be falsehoods because they're not both true together. Okay. So this is going to be an important piece of the puzzle, right? That's going to be very important. That's when our premises are both happening at the same time. Okay, so that's going to be very important. But now let's head over to our conclusion here. Our conclusion is going to be right here, not R, then not P. So we need a not R column, which is just take the opposite of every entry of the R column. So instead of TF, TF, TF all the way down, it should be FT, 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 FT. That's the negation of R column. FT, 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 FT. The negation of the P column, hopefully you just negated every entry in the P column. So instead of 4 truths and then 4 falsehoods, you'd have 4 falsehoods. Let me get my color correctly here. And then 4 truths. Let's grab the right color here. This is the negation of P. And so we're going to have 4 falsehoods followed by 4 truths. Okay, so then putting those together for our conclusion, if not R, then not P, that should only be false if not R is true while not P is false. This is not P here. So when is not R true? Here it is in the second row. And at the same time, not P is false. So that would be a falsehood there. Does that ever happen again? Yeah, again in the fourth row here. That's a falsehood. And that looks like the only other time when you have not R as true and not P as false. So we're going to say the rest of them are all truths in every other case. All right. So now we have our conclusion column here. So our conclusion column is right here. So now the last thing we need to do is to see if this is a tautology, right? Is this always true? Well, for an if then to be false, the first has to be true while the second has to be false. Does that ever happen? In row 1, we have true and then true. In row 2, we have, and row 3 and row 4, the first one is false, so we ignore that. That can't be a falsehood. But in row 5, we have a truth followed by a truth. That's okay. Row 6, we can skip because that's not even a truth for the first. But in rows 7 and 8, there are truths for the antecedent, but they're also true for the consequent. So this is, in fact, a tautology. True, 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 true. So because this is a tautology, we can say that this is a logically valid argument. Okay? And again, you could have also done this by the Law of Syllogism. Why? Because in reality, not R implies not P is equivalent by the contrapositive to P then R. Okay? So take a look at this slide again and again until you really understand what we did here before you go ahead and move on. All right. So in our last slide here, I just wanted to summarize what it is that we've been talking about. We've been talking about whether or not an argument is logically valid or invalid. Now notice that's not the same thing as whether or not a statement is true or false, right? Valid or invalid reasoning is based upon assuming the premises to be true, the conclusion should follow logically, right? Whereas a statement is true or false based on the actual facts on the ground. If you have time, I encourage you to check out the fun video that I've attached to your interactive notes. That will actually go through more examples with you and from another perspective, from another person who's taught the course. And I think you'll find it very interesting to really make sure you understand the difference between valid and true. If you have any questions, feel free to reach out to me. Otherwise, happy practicing, because math is not a spectator sport. I'll see you next time.